Swayam Prabha. Digital India. Educated India.
Hello everyone. So, now our present topic is uniformity of mixing or blending. So, we have seen that in blow room or in at different places in the short staple spinning process, we can blend two different types of fibers or sometimes more than two different types of fibers, but the blending, whether the blending is properly homogeneous or not, that has to be assessed. So, at present session what we will discuss, how to assess or how to actually evaluate the uniformity in mixing and how to express those uniformity in mixing and blending. So, there is a system which is actually called tandem mixing. This is nothing but instead of only one set of chambers, the output of that chamber, that is a first set of blending process, it again it is fed to the second process. So, this is a first process and second process. So, when we actually the mixed or blended product which we get from the first process, we transfer it to the second process in the similar fashion, what we will get? We will get more intimate mixing at the initial stage itself before carding. So, at the blow room stage, at the mixing line, we can get more and more opportunity, higher opportunity to get the homogeneous blending. But main problem with this type of system is that you need a larger space, even capital investment will be more, and it may actually sometime damage the fiber due to repeated opening, repeated action of fibers, but this results very homogeneous mixing. So, Taft blender is which is proposed by Trussler, it actually contains different segments. So, this is a material reserve trunk where material is reserved, then feed roll with tray, this is feed roll where the through which the material is fed, then opening roller is there after feeding the here the feed roll and tray system is there, then it comes to the opening roller, toothed opening roller which opens the fiber to a smaller tuft, and here you will find the closing trap, closing flap is here where we can control the feed material. Okay. And if it is actually in the weighing plan, it is then is the material goes to the weighing plan. So, where in weighing pan based on the prerequisite weight or mass of material, the closing flap opens or closes. Okay. So, that it controls the delivery of material from the reservoir. Okay. Then bottom trap is there, this is 6 is bottom trap where which controls the fibers from the weighing part. Weighing pan is there. So, from the weighing pan it controls the fiber to the Taft blender. Okay. Taft blender here, this is the Taft blender. So, it in this process it is actually proposed that it gives the proper very minute control of the fiber mass. Okay. Here and opening action is there, which actually ensures the taft openness, increase in taft openness. So, that during the blending, when we blend, this will help intimate blending. So, superior and consistent blend we can achieve through this because of this opening and precise weighing. Precise weighing we can do here, okay, and precise control through the opening bottom trap. So, the accuracy what we can achieve is down to 1% fiber content. Okay. So, that we can see that it is a highly accurate. Okay. We can have the blend proportion very accurate within 1% of the fiber content, and precise relation of blend ratio within less than 1% deviation. It is a very high precision. So, if it is say we want to have 50-50 polyester cotton, in that case we can have say maximum, so 51:49 like that. So, that is a very high precision we can achieve with this type of system. Now, another system we will discuss. So, before that, so this is highly flexible customized system suitable for all application. So, this system is highly flexible, we can use different types of fibers, because here the different fibers are treated at different segments. So, we depending on the type of fibers. For cotton, suppose cotton and polyester we are blending, their cotton, if cotton needs higher opening action, so greater opening action, so that we can control this speed of opening roller accordingly. So, that it is we can actually customize the application. Okay. So, depending on our different blend ratio here, if we it is if we have to change the say 50-50 to 40-60 polyester cotton, in that case also we can change the delivery accordingly. Now, in Ritter blend system, it is a uni blend. It enables the fiber components to be blended very precisely. Again, it's they are also claiming it is within less than 1% this blend we can variation we can have. In this system we can see, suppose here it is a 4 different types of material, it is shown by different colors. So, here if we see here, so this is chamber 1, 2, 3, 4, chamber 4. So, at different fibers from different bales or different components of fibers like polyester, cotton. So, they are fed at different from the different channels, and they are falling through the upright chamber. So, that in the chamber it is for, and then it is here it is a conveyor. Now, we can see the fibers, which is this is exhaust here material feed is there. So, material feed here, then it comes out to be that here it is a 2, this is the material feed, dedusting is there. So, we have some dedusting mechanism. So, which actually remove the dust from the fiber, and then metering unit, here it is a metering unit is there, which actually precisely control the fiber flow. And suppose we want a particular blend or this here we can control the fiber flow, and basically if suppose one portion its metering is thicker, another portion is thinner, if we cannot control, then it affects the blend proportion. So, the metering unit is very important in this case. So, this is the metering unit here, and it is actually there for all the this heads. After that, the component layer, these are the different component layers. So, suppose in this picture it is a 4 different components are there. So, that layers are there, that means the which is further from one chamber 1, the layer will form at the bottom layer, that is the bottom layer will be formed, and from the 4th layer which is close to the delivery side, it will form the top layer. So, that these are the different layer, and then it goes to transport. There is a transport fan is there. So, which will create the suction. So, that fibers will be sucked through this channel and it goes to the other next process, and this there is a control unit which controls the movement of fiber, amount of fibers, and here is the opening unit. This opening unit, that's in the according to this picture, fibers from 4 different feed channel. So, 4 sheet it is coming together at the exit point where the opening unit is there. This is the opening unit, it opens the fiber and mixes the fiber at this stage, and then the mixed fiber, the tufts, different tufts are being sucked here, and it is actually then moving towards the next process. Now, here the advantage is that high volume blends are, for example, 50% cotton, 50% polyester, and high consistent quality at high production rate over long period. So, here we can have very intimate blending and consistent blending. There is actually very low blend variation. Okay. So, that is achieved in this instrument. So, recycling a precisely defined amount of waste. So, what we can here the amount of waste fibers into the process reduces the cost of closer to the and since it is a closer tolerance are worked with. That means, here we can use the recycled fiber with a precise quantity. So, that we can use in this instrument. Now, here we can see the blending controls of different origin and different prices in order to reduce the cost. So, here we can have we can blend the cotton from different varieties, okay, and precisely. So, to reduce the cost we can use the some quantity of low cost cotton with the normal cotton to reduce the price, and here blend precision is very good. So, if you have high precision then the advantage what we will get, so every cross section we will get the proper equal blending. So, if there is unevenness, then the suppose weaker fiber will have, if there is a cluster, then the quality will get deteriorated, because at that point the breakage may take place. So, what happened if the blend is consistent throughout the yarn, so then quality will, overall quality will be maintained. So, even if we are using the inferior cotton. Now, in this picture we will see the its comparison between uniblend with the normal weighing hopper system. So, now in the left side here in this is the normal common weighing hopper system. So, weighing hopper system is there where the weighing system is not that precise at this stage. So, that fibers are not evenly distributed from the weighing hopper, which results the fiber layer in this fashion. Fiber layers are not arranged evenly. So, these are the fiber layer, the one layer say like in blue color, and if you see in the green color also this type of feeding is there. So, that means feeding from the weighing hopper, it is not uniform, because there is no beater and it fibers come in a form of lump. And what happened, if these fibers are layers are superimposed, then what we will see at this point, the green portion is thicker and the blue fibers are, it shows it is a thinner portion. So, here you will see the blend ratio is disturbed, it is basically say 30%, 70%. Now, on the other hand, at other state here you can see here the blue portion is thicker, but green is thinner. So, here if you see the blue becomes 80% and green becomes 20%. So, within this layer it is actually blend proportion is changed. So, this problem will actually continue throughout the process. This actually this after delivery the things will go in on the sequential manner. So, this problem will not be, actually it is very difficult to rectify this problem. So, better care has to be taken here. So, that is a problem of weighing hopper system, but UniBlend they have got a unique feature of opening the fiber to a smaller tuft, and after opening what happened, it is actually fibers are laid on the conveyor with uniform manner, precise manner. So, here if you see the layers are almost parallel to the thickness variation of each layers are very minute, it is almost nil variation it tries to achieve. That is how, if you see, if you want to achieve 50-50 blend. So, here we are actually achieving 50-50% blend in every stage. So, if you see here, so now here if you now try to see the yarn cross section. Yarn cross section is at from this weighing hopper, that yarn cross section we get this type of yarn cross section, where different fibers are actually distributed within the cross section in the cluster form. This is the cluster form. So, up to it goes up to the yarn stage, but Ritter UniBlend system you can see here, it is basically it gives very uniform blending. So, most of the fibers there is typical, this is a typical cross section of yarn, where it shows that fibers are distributed evenly in the cross section. So, this gives a very uniform yarn, uniform blending also. Now, if you here we can see this is actually this portion is enlarged here, okay, metering system. So, here the problem, the main advantage is the metering system. So, very precise metering system, that means you can control the amount of fibers per unit time to be deposited here. So, if we can precisely control the amount of fibers to be deposited, then we can actually control the thickness. So, thickness control here it is very important. Now, let us see here, this is the pressure cylinder, this is pressure cylinder here, and the pressure cylinder what it does, it actually allows the this linear potentiometer which actually measures the linear movement of the system, and opening roller, this is opening roller is here, frequency controller is at this here, it you have frequency controller and microprocessor control for constant metering. So, here it is a this is microprocessor control. Now, this actually cylinder, the pressure cylinder, what happened, it moves the this one actually here the fiber is coming from this side, and this controls the fiber movement, fiber amount of fibers to be presented to the opening roller, and that actually helps the proper uniform distribution of fiber. So, uniform delivery of fiber from the this opening roller. Okay. So, blend homogeneity is expressed. So, here you will get the proper blend homogeneity. Now, we can see here these two yarns, they have different blend homogeneity. Now, this is by visual observation we can make out, but we have to express this blend homogeneity. Here I can say this is the high blend homogeneity, here the homogeneity is the its lowest homogeneity. So, this we have to express. So, blend homogeneity is expressed as it is a degree of mixing. Okay. Degree of mixing is of two types, one is radial distribution of fiber, another is rotational distribution of fiber, that I will discuss. And next is the another way we can express, it is a index of blend irregularity. So, these are the two ways we can express. Now, section of draw frame sliver, you can see draw frame slivers are here. Now, two types of draw frame sliver, this is the now, so this is one, this is a section of draw frame sliver, this is the taft blended draw frame sliver, and this is the draw frame blended draw frame sliver, and this is taft blended. You can see when we do draw frame blending, as we have discussed, if we see the cross section, this is white fiber and black fiber is viscose and white fiber is cotton. Black viscose and white cotton are mixed here. And in draw frame blending we can see the cluster formation are there. So, the intimate blending is not possible. Okay. And even after second passage, after first passage it will be worse than this. But when we blend the fiber in blow room stage in taft blend formation, here the intimate blending takes place. These are the fiber cross sectional view. Within the sliver you can see the fibers are distributed almost homogeneously. So, taft blending will give the better uniformity. So, taft blending, blow room blending shows better blend intimacy. So, it is a very intimately blended. Okay. So, a statistical parameter to estimate the inherent intimacy of blend is, this is the gamma, where and this is the gamma developed by Dever and Walker, and G is the actual number of groups of white fibers in a given section, actual number of fibers of white fibers in a given section, that is a G, and Gx is the number of groups of white fiber at infinite doubling. That means, if you are doubling infinitely, that when you are getting the very intimate blending, in that case G, this is the number of fibers in that group. So, what we get that, so N is the number of fibers in average cross section, this N. So, this N is the number of fibers and P is the average proportion of white fiber in the blend, and 1 by 1 minus P is the average proportion of black fibers in the, that is the probability of a. So, this proportion of white fibers and proportion of black fiber. So, gamma, the parameter gamma is actually, it is a one for random distribution, random fiber distribution, and less than 1 is a poor mixing, okay, and more than 1 is the close to perfect mixing. Now, what does it mean? G is the actual number of groups of fibers of white fibers in a given section, and Gx the number of groups of white fibers in a infinite doubling. So, if you have infinite doubling, so that means it is going to be the random distribution. Here some random distribution will be there. This is the one fiber, another fiber is that. This is also not perfect blending, but it is a random distribution. Random distribution, in that case you have after infinite type of blending, that doubling. So, we get this type of process where G and Gx are same. But if you go on increasing the perfect blending, so or if you try to do from the back from our this flock feeding and bloodroom side, we can also achieve little bit more, but that random blending is random fiber distribution is enough if we can achieve, okay, for this short staple fiber mixing. So, this is radial distribution. In radial distribution what happened? Fibers are actually distributed evenly, but what we measure? We measure the blend proportion at different section in the annular cross section. Okay. So, in this cross section we will measure. So, along the diameter of the fabric, sorry, the yarn, this is yarn cross section, and in this yarn cross section at the core we will try to measure the blend proportion here. Suppose polyester cotton is there. So, what we have to do? This is the polyester cotton yarn. At core we will first measure the blend proportion, then we will take the next layer, okay, next layer, then third layer. So, in this way we will keep on taking the blend proportion of that those layers. Now, here how do we take this one? We take these things, that there is two possibility. So, here we can use the same thickness of each layers of same thickness that we can take, or we can take as equal area. So, if we want to have equal area, so same thickness means this is the cross section of yarn. Now, what we are doing, this is one, okay, and the thickness will be so equal to diameter. This is d is diameter. So, the same thickness will be there, d, again this is diameter, this is the diameter d. So, same thickness we can take, but in this, that is the one approach. Another approach is that same area. Now, to have same area, this is one area 1. Now, area 2 will be area 2. So, this is 1, this is second layer, third layer. So, you will see as we go on close to the surface of the yarn outer core sheath. So, the thickness will keep on reducing to maintain the area. This is different, another approach, and here at different zones. So, at different zones we will have different blend ratio. Now, we can see this is one typical example. This is typical example of a blend ratio test, where we can see at different zone the fiber distributions of blend ratio are different. So, that is the study that we can get, but our ideal blend distribution should be equal. So, all the sections should have equal blend ratio. Okay. okay, blend ratio. Okay. This is different zones. At different zones the blend ratio should be equal, that is the ideal case, but we get accordingly we can measure the blend distribution, blend ratio here. So, that this variation, from this variation, higher the variation, that means inferior is the blend quality. Okay. Now, this is radial distribution, another is rotational distribution. You can see this is the rotational distribution here. So, what we do, we actually divide the cross section at different zone. Here in this case we have divided into 4 different zones. One can divide it to many other zones. So, say 8 zones we can divide at different 1, 2, 3, 4, 5, 6, 7, 8 different zones, and we can see the blend proportion at different blend ratio at different zones. So, here you can see here. Now, again, so the blend ratio of this one is this one, 2 is little bit high, 3 is lower than that, and 4th is very low. So, that we can achieve, we can see, but again ideally the blend ratio for all the section should be equal. So, depending on our requirement, we can see for say draw frame blending, this method is actually adopted, because the fibers are different color different slivers are actually placed side by side. So, this method is suitable for draw frame blending, and other blending, for other type of blending, that radial distribution is suitable, but you can use any of the methods. This will give you the distribution of blend ratio. So, ideal case blend ratio same for all zones, that is the ideal case. Now, we will discuss another method which term, which is index of blend irregularity, IBI. What does it mean? The IBI assesses how well the different fibers are distributed within the yarn cross section, which indicates whether the blend is uniform or if certain fibers tend to cluster or migrate. So, that we will see whether there is any cluster is the formation is there, whether the fibers are migrating from one place to another place, that we get from the IBI, index of blend irregularity. So, how can you use? A low index means the blend is uniform, okay, and with fibers of different types evenly distributed throughout the yarn. So, higher IBI, index of blend irregularity, means it is not uniformly distributed. So, higher IBI value suggests that the blend is less uniform, with some fibers tending to cluster formation. So, for draw frame blending, the IBI will be higher than blow room blending. Okay. So, that is because the IBI value is indicates the lower IBI means your more intimate blending. Okay. So, what are the factors which affect the IBI? So, IBI can be influenced by many factors like blending method. So, flock blending versus draw frame blending, I have already mentioned that means flock blending, this is the draw frame blow room blending. Flock blending gives the lower IBI than Dwarf blending. The type of fibers used, like type of fibers used means your if fibers are having higher cohesion. So, they will form the actually lower IBI. Okay. So, more uniform. So, lower IBI, so that will they will have the higher IBI if the cluster formation is there. There are different fiber, like depending on the crimp. If the crimp is too high or crimp of the fiber is too low, as we have mentioned in last class, that this will form the cluster, and cluster formation means the IBI value will be high. So, for those type of fiber, proper crimp is to be set. The spinning process, in the spinning process, as we have already mentioned, that proper metering, if it is not there, proper opening fibers are not there, in setting if it is not kept properly, in those, in that case the this IBI value will be high. Okay. So, importance of in textile manufacturing. So, understanding this actually IBI, so index of blend irregularity, and controlling it is crucial. Actually, it is very crucial because it controls the quality of the product. If we do not measure this IBI, and suppose there is a yarn, this is yarn, okay, and in this yarn, now I will draw. So, this is the polyester fiber, very high IBI, and this is say cotton. So, cluster formation is there. So, in that case, if we dye, the dye uptake of polyester and cotton are different. So, they will form uneven dyeing. So, dyeability will be a problem, appearance will be problem, and even strength distribution. So, different at different zones, suppose here the fibers are polyester is high. So, in the next session it is cluster formation, the cotton is predominant. So, in that case the strength it will get affect. Okay. So, research has shown that flock blending generally leads to better IBI, that means it reduces the IBI, more uniform blending compared to Dwarf blending, especially for blend like polyester viscose or polyester cotton. So, flock blending is very good, and Dwarf blending it will definitely have higher IBI value. So, this is the relationship developed by Copeland and Klein. So, IBI is the relation, this is the relation where Ti is the total number of fibers in a given section. So, if you see the cross section, total number of fibers in that section, and Wi is the number of fiber component W in that section. Suppose we are taking one particular section, just like I will tell you, one section we have taken. Now, here total number of fibers, this is the total number of fibers, okay, T. Here suppose total number of fibers are 100, okay, 100 fibers in the cross section, and W1 is the number of fibers. So, say W component fiber, it is a, this is Wi. So, 30 fibers are there Wi in say polyester, and average fraction of component W for all section. Now, this is one section. Now, the yarn is having total at different section. Average fraction is P. P is the average fraction of all sections. Okay. So, one is that particular section Wi and P is the average of that W component in all the sections. Okay. And Q is the in other fiber 1 minus P. M is the number of section examined. So, M we have suppose this is one section, another section 2, section 3. So, that it may be in radial fashion or it may be in rotational fashion, that we can check. So, different sections are there. In our earlier case we have seen 4 sections were there in that. So, this is it is a rotational 4 sections are there. So, M is the number of sections and IBI is more than 1, that means it is a less homogeneous. Okay. IBI is equal to 1, it is a random arrangement, and IBI is perfect blending, IBI is 0 value. So, as we know that lower IBI means it is better blending. So, that if it is more than 1, that means less homogeneous. For say draw frame we get IBI more than 1. For flock blending we get 1 or less than 1. Okay. That is flock blending. Now, blend evenness, how it is we are getting. So, evenness in longitudinal direction. So, if we get, so we have seen the index of blend irregularity. Now, how the blend evenness affect the material. Suppose in longitudinal direction, this is one yarn, it is a polyester cotton yarn. Now, if you see in longitudinal direction, these are the polyester fiber. Okay, this is polyester fiber, and here polyester fiber is less, and we are getting the cotton fiber. Here cotton fibers are less varied one, but polyester is dominating, sorry, cotton is dominating. So, you can see the longitudinally there is a variation. So, here this is a cotton rich and here it is a polyester rich. Now, after making fabric, if we dye, we will see the appearance will have, this will have different appearance. This will produce a strip of one cotton, colored cotton and colored polyester. So, that will have strips or bar, it will give uneven, patchy, uneven appearance of fabric due to uneven dyeing. So, but there will be definitely variation, we cannot eliminate the variation, we cannot have perfect blending. So, there will be some allowable, this allowance should be there. So, plus minus 3% is allowed. Okay. That means, if we have polyester cotton blend 50-50 it is a target. So, we can in extreme case we can allow 43, 45, 7, 53 or 53, 47, plus minus 3% we can, the variability we can allow. Now, evenness in cross section, the homogeneous blend, earlier we have seen that evenness is cross section. So, in blow room blend we can get the homogeneous blending in blow room and also for rotor yarn. Rotor yarn, what happened even after sliver, in rotor yarn during opening action by opening roller, the fibers are mixed intimately and deposited in the rotor groove and form the yarn. So, this yarn cross section, in the yarn cross section fibers are distributed evenly, and radial blend, the core sheath type blend is also there. So, that is one is homogeneous blending, another is that radial blending. So, here you will see in this core zone, suppose it is a polyester ditch and here it is a cotton ditch. So, this type of core sheath type of structure we normally sometime try to intend to get for some special purposes. Okay. Sectorial blend, so that is pore sliver blending. So, these are different sector we try to see the blending. So, that is in a draw frame we can get segmental blending, bed sheet blending. So, these are the different blend evenness in cross section. So, homogeneous blending, radial blending, sectorial blending, segmental blending. So, all this type of the blend or blend unevenness we can actually achieve for with a different process. Now, let us discuss the different process through which we achieve this different types of blend evenness or unevenness. First, homogeneous blend, it we achieve in blow-room blending or rotor blending. So, if we use if we blend the fiber in the blow-room stage and the yarn, what we will get? We will get almost homogeneous blend, and even we do the draw frame blending and draw frame blending up, and after that if we form the rotor yarn, still we will get the homogeneous blending, because there will be intimate blending during at the opening roller. Now, we can see this is and we will get the cross section. So, there are two components and component A and component B, and homogeneous blending we will achieve in this fashion. This is the homogeneous blending where we get the in the cross section we will get the fibers distributed evenly in the cross section. Now, radial blending, and this is a core sheath type of blending. Okay. Now, you can see here component A preferentially actually going to the core, and component B it goes to the surface. Now, this is actually this type of faulty blend or radial blend core sheath type we achieve even after the blow room blending. Even after blow room blending, if we select fiber with different nature, like widely different linear density, widely different denier of the fibers, if we use the coarser fiber will always have try to come into the sheath, and finer fiber will have the or even a fiber with different bending rigidity. So, this will come try to come in the sheath, and even longer fiber, even fiber length if we mix at different fiber length in the yarn, the longer fiber will try to come to the migrate to the towards the center, and the shorter fiber will try to migrate towards the sheath. So, that is why in polyester cotton blend we try to maintain the length of the fiber. So, 38 millimeter polyester is taken, not the longer polyester. So, to avoid this type of blend non-uniformity. So, radial blend, that is core sheath type blend, is useful when the core is synthetic and sheath is natural. So, this is also important. We try to achieve in some, deliberately we try to achieve this, because suppose we try to achieve for apparel textile, the cotton and polyester we try to blend. We want the cotton to be in the sheath, because it has got very good feel, okay, for soft feeling, and it absorbs moisture. So, we try to be the cotton to be in the sheath, and this is polyester to be in the core. In that type of requirement, we try to achieve this type of blending, the radial blend, it is deliberately we can achieve. Okay. And sectorial blend. So, in bloom blend, in drop-in blending, so in sliver blending, if it is poor, then we get this type of sectorial blending. At different sector we achieve. Suppose in a draw frame, if we suppose in the draw frame we are having say 8 slivers. So, this is component B, and component A. So, these 8 slivers are fed in the draw frame. Now, when the slivers will be drafted, they are not migrating from one place to another place, they are not migrating. So, what they will form? They will form this type of sectorial blend, and that is actually the with a high blend irregularity. So, it is not suitable for most of the applications. So, the sectorial blend is not suitable, although the core sheath type of blend is suitable for a particular application, as I have already discussed. Now, another blend is that segmental blend type. So, where we actually blend the sheet form, like in the lap form, if we blend it actually form a different sector wise. This is the different sector. We can see component A, they have sector, and component B. So, in the sheet form if we blend, we get this type of blend irregularity. Now, segmental, that is this at different segment. So, segmental blend is also unacceptable and not suitable for most of the use. So, this type of segmental blend also achieved we can get from the drop-in blending also. Okay. Now, the handle and comfort appearance. So, blend evenness, it affects the handle, comfort and appearance, that I have already mentioned. So, if you want to have proper handle, so that we can preferentially we can put the natural fiber at the surface, but if it is not even, then appearance will be poor, cost will be there, tensile property will get affected. So, higher blend, that is your blending, homogeneous blend will have better tensile properties. So, the basic crux of the say is that is the homogeneous blend is the optimal and should be aimed at the at most of the cases. So, we always try to achieve the homogeneous blending, and that is that we can do from different process, but blending at bloom stage is very essential. That is why most of the machinery manufacturers they target they are actually their development is mainly at the flock feeding or blending at that stages. So, to achieve the if we can control the fiber feeding at that stage, we can achieve proper blending. Okay. So, we will stop here and we are closing the blow room part. So, next session we will start the next process, which is carding, mechanics of carding. We will start in the next process. Till then, thank you.